We worked with resistors, capacitors, and measured current and voltage. So let's break it down. Before we jump into the experiment, these are some key formulas we used. The first one we used to find the time constant. It's the voltage decay in an RC circuit. You take the ln of delta V over your V naught for your voltage, and you set that equal to your negative T over RC in order to find the time. The other to know is that a resistors in series is for the R total is equal to R1 plus R2 and so on. Resistors in parallel, the 1 over R total is equal to 1 over R1 plus 1 over R2, etc. So the goal was to understand current and voltage in circuits with resistors and capacitors. So we had three main goals in this experiment. The first was to measure the electric current and voltage in the DC and RC circuits, to find the time constant using experimental data, and then finally to compare the experimental and theoretical values. As a brief overview of the main result, we calculated the resistance at the wire of being 0, the R47 resistor as 48 ohms, and the R100 as 102 ohms, and then with the ammeter we had that equal to 0 ohms. Right below this picture shows the loop and node rule that we also used, where the sum of the voltages is equal to 0 in a system, and the sum of the I's is equal to the output, which is equal to the input. The experimental time constant that we got was 5.8, and the computed time constant that we got was 6. So we had the setup as such with the circuit being the system. This is for part 1. The surroundings being everything outside the circuit. And for the procedure setup, we had two 1.5 voltage batteries, two resistors in series with 47 ohms and then 100 ohms, and two ammeters set up in between. The initial conditions of part 1 led us to find the experimental value of the current at 0.02 amps and the actual value of current very accurately at 0.02 amps. So for data and calculations, the change in voltage is based on this graph below, with A to B equal to 3 volts, D to E equal to 0, G to H equal to 0, B to C equal to 0 volts, E to F equal to negative 2.04 volts. This is the way we drop. And then H to A as 0.0 volts. And then in between that, the C to D had a drop between negative 0.96 volts. And finally, the F to G was 0 volts. For resistance, we found, this is the calculations we used to find those ohms. The R47 resistor, we simply did the negative 0.96 from C to D divided by the 0.02 amps to get 48 ohms. And the R100 resistor, we did negative 2.04 from the E to F and divided that by 0.02 amps to get 102 ohms. And once again, the R of the wire and the R of the ammeter was 0. In this part of the experiment, the source of error could have been the imprecision of the ammeter reading or just rounding calculations, since we were rounding to the third decimal point for a lot of these. Second, I mean. And then we set up the second part of the experiment, which was the RC circuit. In this, the system was the RC circuit and the surrounding was everything outside. The initial conditions that this was performed under was with a 9-volt battery, 2 light bulbs, one 10 ohm and one 20 ohm, and one 0.2 Faraday capacitor. The entire procedure was repeated once with a 10 ohm light bulb and then once with a 20 ohm. So the procedure was essentially to measure the time it takes to charge and discharge the capacitor. In this, the predicted RC was equal to 6 seconds, and the experimental RC is equal to -1 over the slope, which we got as negative 0.1724, and we set that, and that equals 5.8 seconds. So it was pretty close. So right off the bat, the source of human error in this condition was very easily human error due to using a stopwatch. There was no possible way for us to accurately be able to stop the time at charging and discharging as accurately as needed scientifically. But essentially, for the R10 bulb, for the charging and the discharging time, we got 16 seconds and then 15 seconds. And the R20 bulb, for charging and discharging, we got 29 seconds to 28.5 seconds. So essentially, there was approximately equal timing in charging and discharging of the light bulb, but it was double the time for double the resistance, which did make sense. So to answer the additional questions of what if you charge the capacitor with no resistor in the circuit, as an ideal circuit, the capacitor would charge instantly with no resistor, but in reality, the battery has an internal resistance, the capacitor has properties, and the ammeter has a resistance that slow down that process. So as a result, the capacitor takes longer to charge than the ideal model predicts, and that's that. So that